Hi, everybody. Can you hear me? Can you hear me in the back? Perfect. So we can bring the lights a little bit down so that we can see the nice slides we have got for you. But yeah, welcome, and thanks for coming to hear about science on such a nice sunny evening. So I will tell you about how we have come through a whole bunch of different milestones to our current understanding of cosmology and the mysteries we uncovered and what we are planning to do to solve those mysteries. So in the last 25 years, we pieced together a model of the universe that describes its origin and its evolution. So this was an audacious undertaking, and you won't be surprised to hear that we haven't cracked the cosmic code just yet. By looking up at the sky, at the largest scales that we can see in the universe, we've uncovered deep holes in our understanding of the fundamental physics describing the smallest scales that we can probe. To solve this cosmic mystery, we need to look at this puzzle from many different viewpoints. And to do this, we are building a multifaceted toolkit that combines data from huge new astronomical facilities with the latest advances in AI technologies and complementary information from laboratory experiments. So I'm going to show you some of the latest developments in these areas that I'm personally most excited about. To start with the most basic point, what makes cosmology possible is that light has a speed limit. It's very fast, but it's finite. This means that light takes time to travel to us even from the closest stars, so we see those stars as they were a few years ago. Okay? So when we look out into depths of space, we can see the universe as it was in the past. Looking at the distant universe is a kind of time travel. So this allows us to look to more and more distant epochs of the universe and see it as it was when it was younger and younger. You can roll back time in this way to the oldest light that you can see in the universe, which came into being 13.8 billion years ago. And we call this the cosmic microwave background. So this map that you're seeing here was a milestone measurement of the cosmic microwave background. It shows a baby picture of the universe when it was only 380,000 years old. So that sounds like a very old baby, right? But remember, it's now nearly 14 billion years old. So this map was made by the Planck satellite, which was launched by the European Space Agency, and it brought the early universe into sharp focus. We measured, using this map, the parameters of the cosmological model to percent precision. An example is, indeed, the age of the universe, 13.8 billion years. And we measured that with percent precision. So this is a question asked by humanity since the beginning of history. So it is an amazing advance that we were able to make. So we can't do experiments with the universe. Cosmology is an observational science. So I want to give you a flavor of how we can use maps like this to learn about the universe. So in addition to making maps like this using data, we can also make theoretical predictions from different cosmological models to what this map ought to look like if that theory was the right theory of the universe. So this map is a kind of fingerprint. So what we can do is that we can compute a whole bunch of different theories and their fingerprint maps, compare those theories with the actual data, and work out which models don't work and which models match the data. And when we do that, what we find is something rather surprising. So all the information in these millions of pixels on this map is described by only 6 numbers. These 6 numbers tell us the shape or the geometry of the universe, its constituent components, for example, atoms, dark matter and dark energy, the age and the clumpiness of the universe, and also some information about when the first stars formed. So it's just 6 numbers. So the model of the universe we've uncovered seems surprisingly simple. But the simple model contains 3 ingredients which are not part of the standard model of particle physics. There's dark matter and dark energy, and the early universe was clumpy. And so what made all of that structure at the beginning of time? So those 3 ingredients are not in our standard theories of physics. So the universe is simple, but it's also very strange. So while we measured these parameters very precisely now, the standard cosmological model remains phenomenological. But what is the physical nature of this dark matter and dark energy? We don't know the answer to these questions yet. They together comprise 95% of the energy budget of the universe. Imagine you were making a budget yourself and you didn't really know where 95% of your funds were, right? So the matter made of atoms, like stars and planets and people, everything in this room, everything we've been able to probe in the laboratory, that's only 5% of the energy budget of the universe. We also don't know where all the stuff in the universe came from originally. So this is a question that animates my research for a couple of decades now. The leading hypothesis is that in a tiny instant at the beginning of time, a so-called scalar field, we call it the inflaton field, caused the universe to expand really rapidly by a factor of at least 10 to the power 26. We call this process inflation. This is not what's happening to the economy. It's what the universe seemed to have done early at the beginning of time. So at the same time as it was expanding like that, tiny quantum ripples in this scalar field got stretched out by the expansion of the universe. And they became the seeds of all of the structure we see in the universe today. So then, 380,000 years later, we see the imprint of those seeds of structure in the cosmic microwave background. And that represents these little ripples in the distribution of matter in the universe that then collapses under the action of gravity to form all of the complicated structures that we see in the universe today, nearly 14 billion years later. So the starting point of my talk is that the study of the oldest light in the universe revealed a simple but mysterious universe. So in the rest of the talk, I'm going to give you a flavor of the new tools that we can leverage to crack this cosmic code. And the first approach I'm going to show you is mapping dark matter with a billion galaxies. So it's worth remembering that it's only about 100 years ago that we discovered that there were galaxies other than our own Milky Way. Isn't that surprising? So in October 1923, the US astronomer Edwin Hubble identified the so-called Cepheid variable star, the first one seen in the Andromeda galaxy. So you might know that the Andromeda galaxy is the closest big galaxy to us. At that time, they didn't know that it was outside our own galaxy. But this observation showed that the galaxy was not part of the Milky Way. So why was it so hard to work this out? So it turns out that measuring distances in an expanding universe is very difficult. So Hubble used an ingenious approach that had been devised by Henrietta Swan Leavitt in 1912, involving this class of pulsating stars that we call Cepheid variables. And this is still one of the most accurate ways to measure cosmic distances today, but it only really works in our cosmic backyard, as it were, because these stars are not so bright and they can't be seen way out in the distant universe. We'll shortly see that working out how far away galaxies are is still a key challenge to using them as cosmological probes. So an obvious way to view the universe is in starlight. There's a reason our eyes have evolved to see the world at optical wavelengths, right? The sun has significant radiation output at those wavelengths. So starting in the 1990s, we've been mapping the universe in starlight in very deep and large-scale galaxy surveys. So this is part of the Sloan Digital Sky Survey. So each one of those galaxies is a real object. There are about 400,000 galaxies in this animation. So for me, the Sloan Digital Sky Survey was the point when cosmology, my field, became a data-driven subject. The full size of this 20-year-long survey is not huge by modern standards. It can fit on a hard drive of about 40 terabytes. An individual researcher can easily aspire to that much storage space. But it was a watershed moment for the automatic acquisition of digital survey data from the sky. So when we map galaxies using light, we see them arranged in this complicated cosmic web. It's because they're tracing huge filaments of dark matter that you can't actually see. So this image is actually sliced through a simulation of how galaxies trace dark matter, and you can't see 80% of the matter in this image. Here is a simulation of the formation of a huge cluster of galaxies. So these are gargantuan structures, the biggest structures you see in the universe. And cosmological simulations like this are a key tool for understanding what our sky surveys are actually showing us. And by using computer simulations, we can make detailed predictions for how galaxies trace the underlying dark matter, and we can calculate different fingerprints for different cosmological models, different theories of dark matter that will alter how galaxies are scattered within this cosmic web. And we can compare those predictions with the data and again figure out which one actually fits and which ones are ruled out. So our understanding of how galaxies populate the universe is about to be revolutionized due to major facilities that have recently come online or are just about to. And cosmologists are gearing for a torrent of data that's going to come upon us. And we are truly in the era of like big tech and big data. And to make sense of that data, we are going to need big algorithms. So the project that I'm personally most excited about is the Vera C. Rubin Observatory's so-called legacy survey of space and time. That's a large mouthful, so we call it LSST. LSST is the ultimate big data project, and it's starting operations just in July this year. The pictures of the universe that we've obtained to date are basically static. They're frozen in time. And Rubin will observe the sky in a completely different way. So it'll return to every patch of the southern sky, so that's half the sky, roughly every 3 days or so, and do that for 10 years. And by stitching together those images at every point in the sky, we will be able to make a movie of the dynamic universe. And this will enable us to study space and time in a way we've never been able to do before at this scale, and expand the surveyed space-time volume by a factor of about 1,000 or so. As a comparison, I previously mentioned the Sloan Digital Sky Survey as a watershed moment in this field. A single sky scan from LSST, which it will do every 3 days or so, will equal the depth of the entire 20 years of the SDSS survey. So it's like a huge advance in our capabilities. So the Vera Rubin Observatory is named after the pioneering astronomer who established convincing evidence of dark matter from galactic rotation curves. And this is the first major facility, astronomical facility, that is named after a female scientist. I think it's about time. And this amazing purpose-built survey facility is on the summit of Cerro Patron in Chile, where the skies are very dark and you can observe very deep into space. So LSST will enable diverse science missions at the same time. So in addition to enabling us to investigate dark matter and dark energy, it will make an inventory of the solar system. For example, it will find near-Earth asteroids that might threaten our planet in the future. Hopefully in time for us to do something about it. It will make this movie of the universe that I described, and it will make a detailed map of our own galaxy, the Milky Way, and thereby enable other tests of dark matter. So the resulting data set is enormous. It's about 60 petabytes of raw data, 500 petabytes of processed data, and it's truly big data in terms of not just its volume, but its rate of delivery and its variety. For example, it will signal to us alerts about 10 million things changing on the sky every night, and we have to look in that huge torrent of data for the objects that we are interested in order to trigger follow-up facilities. So it's a huge data analysis problem. So I was incredibly lucky to be able to visit Rubin while he was still under construction. So that's in December 2023. I got to go to the summit and see it. It was truly incredible to see how the engineering drawings that existed when I joined this project in 2013 had come to life. And it's a reality, and now we have to prepare for this data later this year. So this is actually, let me play it, it's a time-lapse movie of the LSST camera being installed on the telescope, and this happened this month. The team on the summit basically used a vertical platform to get the camera up to the top and then install it in the telescope. So you can see, that's where the camera is going up. And then they brought it in with this very specialized, very accurate rig, and they installed it very carefully into the telescope. And all reports say the data will look really amazing. So this is the largest digital camera ever constructed. As you can see, it's the size of a car, a big car. And it'll observe the sky in huge 3.2 gigapixel images. Each one of the images will be 3.5 square degrees. This is roughly the size of about 40 times the size of the full moon on the sky. So huge, deep, very clear pictures. So one of the most powerful ways we can leverage this huge galaxy catalog is to map dark matter with gravitational lensing. So in Einstein's theory of gravity, mass bends light. So this image shows how dark matter in a massive cluster of galaxies, like the one that I showed you in a simulation earlier, so that cluster is in the foreground, and it's lensing the galaxies in the background, and the lensing effect stretches out these images into multiple images and arcs. And looking at it is a little bit challenging to understand how that happens. Since we're in such an old school venue, I decided to show you an experiment that one of my colleagues at the Cavendish Laboratory, Malcolm Longair, devised some time ago. So you can see that there is this lens in the foreground, right? So it's not a normal lens. It's shaped like the gravitational potential well that you would expect from a cluster of galaxies. So now, hopefully you can see this starting to move across a boring grid to start with. And you can see as this cluster, this mass moves across this grid, like if you look down the barrel of the lens, there are very, very strong lensing effects. That's called strong lensing. But what we want to do, okay, so now it's going across a galaxy field, and you can see, hopefully, similar streaks and multiple images like you saw in that astronomical image from the Hubble Space Telescope. So we can use this strong lensing effect to map dark matter, but what I'm particularly interested in is what's going on in the outskirts. So as photons travel to us from distant galaxies, their paths get very slightly bent by massive dark cosmological structures that they encounter on the way. And this is called weak gravitational lensing. So weak lensing of galaxies by the intervening dark matter distorts their shapes only very slightly, like by about 1%, and also displaces them. You can back out this effect of distortion to map dark matter over cosmic time and work out how the matter in the universe is actually evolving. But if you don't have an accurate estimate of how far away galaxies are, you will not measure the amount of distortion accurately. And therefore, you will not work out how much of the intervening mass is there at each distance that you're probing. So that means you get a distorted measure of how matter is evolving under gravity in the universe. And that means you'll reach wrong cosmological conclusions. You'll get a wrong answer for your cosmological model. So we've come back to the problem of working out how far away things are in an expanding universe. A really good way to find this out is to measure what's called a redshift, which I'm going to illustrate to you now. So this is a wonderful example of a rainbow, which I photographed a few years ago in Iceland. Here, the water droplets are splitting sunlight apart into its constituent colors, which are characterized by different wavelengths. So that's what's shown here. This is the spectrum of the sun. This shows how the light is distributed as a function of wavelength. So you can see the bluer colors are at the shorter wavelengths, and the redder colors are at the longer wavelengths. So if you were to look at an incandescent light bulb, like this one that's shining at us, through a diffraction filter, you can break its light apart, and hopefully you can see that this incandescent light bulb example here has kind of a rainbow in its spectrum. It is a rainbow, but it's a different emphasis of reds to blues compared to the spectrum of the sun. So now we want to look at a hydrogen bulb. So hydrogen is the most common element in the universe. In fact, most of the atoms in the universe are hydrogen atoms. Most of the rest is helium. And astronomers call all of the other elements in the periodic table metals. They're like a couple of % of the contents of the universe, all the carbon that composes us, it doesn't matter, metals. Anyway, we want to look at hydrogen because hopefully that is a good way of learning about where stuff is in the universe. So it may be interesting to look at light from a heated hydrogen bulb through a diffraction filter. And if you do that, this is what you see. So it's not a rainbow, as you can hopefully see. You should see 3 lines here, okay? And there's a blue line, a red line, and a very faint violet light, which may not be coming up in this particular, no, I can kind of see it. All right, so if you plotted the spectrum of that, yeah, you see 3 lines. They're violet, blue, and red. And these particular spectral lines are part of the so-called Balmer series of quantum mechanical transitions in the hydrogen atom. So why is this story interesting? Spectral lines like this are crucial to measuring redshifts. So in the laboratory on the Earth, we know exactly what wavelength these spectral lines should be at. This is fully determined by quantum mechanics, and when we observe the same lines in distant galaxies, if you go further and further away, we see the same lines shifted to redder and redder wavelengths, longer and longer wavelengths. Why is that? It's because the wavelength of the light is being stretched out by the expansion of the universe. So by measuring the position, the wavelength of the line that you see in a distant galaxy with reference to its position in the laboratory, you can work out how far away something is. So done and dusted, right? Can we go and take spectra of 1 billion galaxies that Rubin is going to observe? The answer is sadly no, not even with our current amazing technologies. We can't get a spectrum of each galaxy in Rubin's billion galaxy sample. Instead, Rubin will measure 6 colors per galaxy. And to be able to do that, to use just the 6 colors to get the redshifts, we need to understand how galaxy properties relate to their colors and their spectra. So in the past few years, a key realization has dawned. To decode the cosmos, we need to understand galaxies. So it's kind of coupling the study of cosmology with the study of galaxy evolution. And this is a challenge because galaxies are the most complicated beasts in the universe. And understanding their light distributions is related to their constituents, their population of stars, dust, and gas that they contain. So imagine that you had a recipe for generating realistic examples of galaxy colors. What ingredients would that recipe contain? So the light that galaxies emit depends on galaxy properties like their mass, their star formation history, their gas, the metallicity of the gas, whether they have an active black hole in their centers, and so on, and their redshift, of course. So fortunately, there is such a recipe that allows you to predict colors of galaxies, and it's called stellar population synthesis. So we can leverage this to solve the challenge. So the idea is that we can work out how far away galaxies are if we solve another seemingly much harder problem, which is to be able to faithfully model the diversity of galaxy properties over cosmic time simultaneously with the redshifts. And this problem is not tractable with standard approaches, especially when you consider catalogs of even hundreds of million galaxies, let alone a billion. However, modern machine learning techniques can accurately describe the complicated web of interdependencies between galaxy properties. And these tools have literally become available in the last few years, essentially over the pandemic. We've just succeeded in the first attempt at building such a model, where the recipe for building a realistic galaxy population is encoded within an AI technology called a diffusion model. So with tools like this at the ready, this is what we can look forward to when LSSC starts later this year in July. So here on the left, you can see a typical patch of the sky seen by the Sloan Digital Sky Survey. And on the right is a preview of what LSST data in the same patch will look like. You can see the level of detail and the kind of step change that is enabled by this new survey. So in 100 years, we'll have gone from knowing that there is one external galaxy to measuring the properties of a billion galaxies. And powerful machine learning methods have become available just in time to do some heavy lifting here. And these tools help us embrace the complexity and the size of the data set rather than fighting against it. And we can use them to help us decode the cosmos. Now I want to switch to a complementary approach to decoding the cosmos, which is detecting dark matter in the lab. So a key unanswered question in cosmology is, what on earth is a dark matter particle? There are many, many creative theoretical proposals, but there are two broad classes of candidate theories: weakly interacting massive particles, also called WIMPs, and axions. These are particularly attractive theories because they were not invented as a dark matter candidate, but rather to solve major problems in the standard model of particle physics. So much of the experimental effort in the past decades has focused on the WIMP hypothesis, and obviously you haven't heard about it, so they've come up empty-handed so far. And it's only more recently that experimental attention is turning to axions. And there's a huge part of the axion parameter space that's relatively unexplored. So the so-called QCD axion is my favorite dark matter candidate. The QCD axion is a compelling candidate because it was not invented as a dark matter particle, but rather to solve a mystery related to the standard model of particle physics, and it's called the strong CP problem. So the standard model has a parameter called the neutron electric dipole moment. It doesn't matter what it is. It's literally a parameter that you have to measure because the theory doesn't predict it. And experimentalists duly went and measured it. And guess what? It's tiny, okay? Physicists don't like fine-tuning. Like, why is it so small? Why isn't it like a number of order 1? So the axion was proposed as a dynamical way to explain this kind of fine-tuning. And it's meant to wash away the problems of the standard model of particle physics, and is actually named after a detergent. So the axion has wave-like properties as well as particle-like properties, and its wavelength is related to its mass. So we can use a very strong magnetic field to induce the axion to decay into photons, particles of light. And those photons will have wavelengths which match the mass of the axion. And when this decay happens, we get a teeny tiny electric current, okay? Which we can read out, hopefully. And the power generated by this tiny current is 10 to the minus 23 watts. That seems like a very small number to compare to something else you might have heard of. So, currently, beyond the edge of the solar system, there is the Voyager spacecraft, which has a 4-watt transmitter outside the solar system. And we can detect that signal here on Earth, and that generates a whopping 10 to the minus 17 watts. So this is truly a tiny signal. So we need to build a so-called resonator so that we can amplify this signal and put it in the cavity of a powerful superconducting magnet. And when the size of this cavity matches the wavelength of the axion, which is related to its mass, you can see a peak in the electric power. So it's a little bit like tuning a radio to find a station. However, we don't know exactly where this mass is, like what wavelength do we need to probe, and what size of cavity we therefore need to build. So one of the things you really need to do is to be able to tune your experiment to different frequencies rather than having to build one cavity for each particular wavelength you might probe in a very broad range. So to be able to tune, you ideally want to break the relationship between wavelength and frequency. And this is the same as giving the photon an effective mass. So we do this using this interesting idea called a metamaterial. So a metamaterial will give any given size cavity a plasma frequency, which can be tuned based on the way that you implement this metamaterial, okay? So in this case, it sounds like a complicated word. It's just a bunch of wires. So rather than having your resonator be a box, it's now approximating a box by a bunch of wires. And if you only have the geometry of an individual cavity to search in, that's like having a radio where you're only able to tune in a very, very narrow range of frequencies, whereas the axion might be hiding anywhere in a very big range of frequencies. So that's a problem with the traditional cavity experiments. But for example, here's a tuning idea. You change the relative spacing of the wires, and that tells you which frequency you're sensitive to, and you can tune over a range of frequencies. Here's another cool idea. Here we call these sails, so they're shaped wires and they're rotating. And as they rotate, you can again enable tuning. So we're currently experimenting with different wire metamaterial resonator prototypes. Here is a PhD student at Berkeley, Heather Jackson, experimenting with a prototype that she's building. Here's my colleague Jon Gudmundsen working in the lab with the postdoc Gagandeep Singh on a different prototype design. This is being built in Stockholm, so this is an international experiment. Notice that these are truly tabletop experiments. They're not like the gargantuan particle physics experiments you would find in CERN. It's literally something that you can do in a lab, in a university lab, and even the magnet you would put this in is the size of a normal room, not enormous. So an experiment of this type, which we call ALPHA, is currently under construction at Yale University, and it'll take data for 5 years, and this will allow us to probe the most compelling range of mass for the QCD axion. So the next few years will be very exciting for axion dark matter. I want to show you the latest tunable resonator design. This is from my colleague Yuno Young, and here, this is so cool. The only moving part in his resonator design is one central rod, which rotates wires in a fixed spiral pattern where you can actually change the wrapping to be tighter and looser in the spiral. So this minimizes the mechanical movements of this thing because it needs to be put into a superconducting magnet and be cooled, and so you don't want stuff moving around in there. So he's reduced all the movement to just one central rod. And so that's how you would tune it. And I really also love how this echoes the spiral arms of a galaxy. So hopefully we will find the dark matter with these kinds of ideas. So I've got a few more minutes left, and I want to go back now to the beginning of the universe. And I want to show you a mind-blowing implication of this theory called inflation, which is the prevailing paradigm for the origin of structure in the universe. If this is a correct description of nature, inflation doesn't just make the observable universe, which is pretty huge. It makes a big universe, much, much bigger than the size of the universe we can see. And even more bizarrely, it will create structures on even bigger scales. It will make other universes. The universes live inside these bubbles, with our universe just being one among innumerable others. This is a direct implication of data that we already have. So in this picture, most of space, on scales much larger than the size of the observable universe, is trapped at high vacuum energy. So what does that mean? So imagine that you are in a landscape of potential energy, okay? So this is a picture I took in the Taurus del Paine range. I like to use this as an analogy. So if you're on top of one of the mountains, you are at a place with high vacuum energy. And if you're up there, the part of space you're in is inflating. And somehow, if you manage to get down to where the water is, that is a place with lower vacuum energy, and there you've stopped inflating and you can make a universe. You can end inflation by tunneling to this lower vacuum state, right? And this is called a phase transition. And it happens via the nucleation of a bubble of lower vacuum energy embedded within a landscape of higher vacuum energy. So this kind of idea could have been the birth event of the universe. However, the main hurdle to even testing these kinds of ideas is that our understanding of this relevant theory is just not good enough. These are really difficult calculations. It's as if the universe took all of the hardest maths needed to describe nature, piled it all into one problem, and dared us to solve it. So there are many assumptions and approximations that are involved in coming to this startling conclusion. And we don't know which of those are justified and which are not. So a new approach that we are taking to understand this theory better is to emulate the same physical equations, but translated within an experiment in the laboratory. So by comparing our maths to the experiment, we can refine our theoretical understanding and possibly come up with new observable properties of the universe. So basically the idea is that you have a system you can't experiment with. You can't experiment with the real universe. But another system you can build, you can experiment with, which under the right conditions has the same phenomenology described by the same physics, the same equations as the original system. And if you can work out what those right conditions are for the physics to match, you can translate the understanding gained from the laboratory system back into the system you can't experiment with, which is the early universe in this case. So we are currently building in Cambridge a prototype in the lab which behaves like a quantum field undergoing vacuum decay in the early universe. The experiment involves macroscopic collections of ultra-cold atoms called Bose-Einstein condensates. These experiments operate just above absolute zero. Our laboratory universe is then transported through this complicated setup into the tiny little box there where you can see it fluorescing. That is called the science cell, and that is where we will do the data taking. I want to show you a system undergoing a phase transition, which is also has a non-trivial link to the physics of the early universe. So this is a Tibetan singing bowl. So a person is now going to strike this with a mallet, and as the mallet, okay, the person is being very slow. All right. Okay, so now they've started, and so, you know, as this mallet strikes the ball, you can see that there are ripples starting to form on the surface of the water. And can you see that it's bubbling? Isn't that amazing? I can't make this work myself, but I have seen it actually working, and it is quite amazing. You have seen phase transitions every time you make a cup of tea by boiling your kettle, but there you had to put heat into the system to convert the water into gas and boil it off. Here we are not putting in any heat. It is the resonance caused by the mallet striking the bowl that actually then starts to resonate with the surface waves, so that a very small change actually causes a big change in the system. Okay, so this is a process called parametric resonance. And yes, it is on one hand just a Tibetan singing bowl. On the other hand, the surface of the water has an analogy with a 2+1 space-time undergoing so-called particle production, which is thought to have happened in the early universe as well, in a process called parametric resonance. So this is a fairly unique collaboration at the intersection of condensed matter physics and cosmology theory. And even just thinking deeply about this problem before they have any data to compare with has led to advances in our understanding of the relevant theories that we are trying to understand, and taken us beyond the standard approaches that were available till then. I want to show you the latest on this experiment as well. So the thing that's on the top left there, hopefully you can see like a red dot in the middle of that chamber. That is the Bose-Einstein condensate cooling. It's fluorescing and emitting light as it cools. This is our clever experimentalists who have managed to engineer a potential to such level of detail that is 25 microns up there, and they can use lasers to confine the atoms in the Bose-Einstein condensate to the level that they can make writing alphabetical characters possible. And we haven't quite got to the stage where we nucleate the bubbles, but the one on the bottom here is without this potential barrier to tunnel through, just the Bose-Einstein condensate confined to that sort of box sloshing around. And that gives you a sense, I hope, of the detail with which we can image this system. So I was hoping to show you actual bubbles nucleating, but they literally had to close down their lab and move to the wonderful new Ray Dolby Center in the physics department. So they have to reset up the lab, and then hopefully we will have data. But in the meantime, I will show you a simulation of what we expect. So on the left, you have a simulation of what the experiment is expected to look like. And on the right-hand side, the analogy with the early universe theory. So this is our best understanding of what we expect to happen. By tuning this experiment in different ways and by turning the analogous knobs in our mathematical calculations, we can see whether our expectations are in fact correct for example, the rate at which these bubbles nucleate and how they depend on different properties of the system, and what is the likelihood of a bubble nucleating here if, say, one has nucleated over here. So through experiments like this, we hope to understand better the very extreme conditions in the very early universe. So I want to end now by emphasizing that understanding our universe requires interlinked progress along many frontiers. This field is driven by technological innovation, which is producing large volumes of data, which we need to model accurately and interpret correctly and contextualize in the context of fundamental theory. And I hope I have managed to convey an impression of how this interplay between theory and observation and experiment plays out. And hopefully I've motivated especially some of the young people in the audience to join us in this quest to decode the cosmos. Thank you very much. I think you're allowed to ask questions. I think that's what they're saying.
Hi. I just wanted to ask what would happen if you were to discover the axion mass. What would happen next in terms of linking that to, say, dark matter in the universe?
That's a really good question. So first of all, if we discover the axion mass, somebody will be going to Stockholm to receive the Nobel Prize. That's the first thing that will happen. And after that, we will link that, the mass and the implications of that mass to how much we expect the axion dark matter to contribute to the dark matter we see in the universe. Why do I say that? So far, we know the standard model of particle physics is very complicated. It has 3 generations and lots of particles, whereas our understanding of the dark sector is modeled in such a simple way that we think all of the dark matter must be one particle. I mean, that is not necessarily the case. So we will have to work out what is the balance between the amount of dark matter we predict through the axion mode, and does that compare and actually explain all of the dark matter we see in the universe in terms of its energy budget contribution. So that will be the next thing that people do. The second thing they'll do is to build different experiments to try to replicate the finding that we might get in our experiment. So both of those things will be the immediate next steps, I would say.
Thank you for your talk, which is very interesting. How does your ideas fit in with the multiverse? How do you explain multiverse with your experiments?
I can't explain the multiverse, but it is an explanation for our best understanding of what we see in the cosmic microwave background in terms of the... so if I go back to the picture of the cosmic microwave background right at the start, you can see that this map, which is in kind of an elliptical projection, Right, you can see these mottled patches on this. These are differences in the temperature in the very early universe. This is a map of the full sky, it's like a sphere open up. And so we can make detailed predictions for the statistics of this distribution of hot and cold spots on the sky, and that directly translates into density differences in matter at early times. And so the theory that can explain this actually implies that it makes a universe that's much bigger than ours, and that process doesn't stop. It's called eternal inflation. So it's not necessarily an explanation as such, it's an implication of the theory. So I personally don't find that a scary prospect, because every time we've looked at bigger and bigger scales, we have found that, everything is not what we expected, and the universe is growing bigger, by the decade, right? 100 years ago, we thought the Milky Way was all there was. Now we are trying to map 1 billion galaxies. It doesn't surprise me at all that there are other universes. But that's a speculation, and I want to find ways to test these ideas. And that's why we are doing those experiments, to try to understand the implications of that theory better. I don't know if that's a satisfying answer, but that's the one I can give.
Hello?
Hello.
Hey, I'm really sorry. My question's going to be really stupid questions. So I've just got a few. So the first one was, so you said the universe is expanding. So what do we have a definition of what it's expanding into? Like, what is beyond the universe?
It's not expanding into anything. It's just
nothing.
Expanding, and there's no center.
But we don't have any idea of what that is beyond it, just nothing.
So in the picture that I presented in the multiverse, our universe is contained inside a bubble of low energy vacuum, and outside is regions of high energy vacuum that are still expanding at an accelerated rate. So in that picture, you can say there's something that's different from place to place. But in the context of just the expanding universe, it's not expanding into anything. This is a kind of misconception that sometimes is given when people try to blow up a balloon and show that the universe is expanding like a balloon. It's not a surface. It's it's expanding around us. If we went away to a distant galaxy and did the same measurements, they will also see it expanding around us, around them. So there is no center, and it's not expanding into anything. If you come to study relativity in my Part 2 relativity class, you will understand.
Yes, thank you. This was great. I'm just a little confused in regards to the smaller experiments that you were doing in the lab to focus on dark matter with the pipes. Can you just kind of explain that again so I get a better understanding of it?
Right, so you mean the dark matter experiment, which is doing the tuning, right?
Yes, yeah.
Yeah, so you want me to explain how it works?
Yes, please, yeah.
Yes, sure. So the axion, if it exists, has a very, very small probability of decaying into 2 photons, okay? So this process is very, very slow. The decay probability is extremely low. So typically you would have to wait several times the age of the universe in order to observe such a decay. Of course, if you're impatient, which I am, I want to see it faster than that. So there, you have to boost the probability of decay by piling many axions into one small volume and pumping it with photons so that you induce the decay. And you can do that by making a cavity which has a resonator, and the resonator is basically usually the size of the cavity. You can see that's a cavity, that cylinder, yeah? So if the size of the cavity matches the wavelength of the photon, which is related to the mass of the axion, then you get a boost in the power that you read out. You can see that little peak, that as you tune, you find a peak in the power. So as I said, this energy that is generated by the decay into the photons is very, very small. So that's why we want to have a resonator system. And then the next step, which was a cool idea that we had in our collaboration, is that rather than making a cavity for every wavelength, you could tune the system. And that's by having, rather than a frequency associated with the cavity, having a plasma frequency associated with the cavity. And so then by changing the properties of these metamaterials, you can actually tune which frequencies of light you're sensitive to, and therefore you tune which masses of the axion you're sensitive to. Is that better? You understand?
Yeah, thank you.
Okay,
yes.
Sure. Anyone on this side? There's a lady down there.
Hi, so we had a question about the other aspects of cosmology where you could implement machine learning models in order to find out more about our universe.
Mm-hmm. That's a really good question. I actually had a slide on our machine learning method, but I cut it for time because I was told I only have 45 minutes. But I can try to explain how it works, okay? So actually, I'm going to try to find this for you. Where is the slide? Here. No, it's not letting me do it. Okay, so the problem is that the number of properties that describe the light from a galaxy is very large, right? You would need at least 16 parameters to describe the colors or the spectrum of a single galaxy, and those parameters can vary to produce spectra associated with many different types of galaxies. Now, if you were to randomly sample these parameters, you would get very unrealistic galaxies that don't exist in the universe. So the way that our machine learning model works is that we set a distribution over these parameters in the form of what's called a diffusion model. If you haven't heard of that, it doesn't matter. It's just a complicated way to capture high-dimensional distributions that can be any shape whatsoever. So each parameter can be related to any other in an arbitrary way. And then what we do is we use that model to draw a mock catalog of galaxies. We apply the noise properties of a survey. We apply a selection cut that describes the survey. And so what can we do? We can make fake data, okay? We can now repeatedly make fake data. And the fake data is then matched to a very deep, very comprehensive multi-wavelength catalog that has 26 colors in it, okay? That is able to constrain all of these properties. So what we do is that we have a 26-dimensional point cloud compared to the 26-dimensional point cloud of the real data. And you try to make these shapes match in these very high dimensions. You can't do this without machine learning, but with machine learning, it's actually quite straightforward. And at the end of that matching process, when we draw galaxies from the original model, we make realizations of galaxies that look like populations of galaxies in the real universe. Does that make sense?
If you had infinite time, infinite money, and infinite computing power, what experiment would you do?
I would make a digital twin of the universe. Short answer.
Thank you for your lecture. I've got a question about the dark matter. Mm-hmm. Why the dark matter is dark? Not visible. The 95% is not visible. Only the 5% is visible. Mm-hmm. Thank you.
Yes. Are you asking how we work out that there is dark matter? Yeah, so one method that I showed is this idea of gravitational lensing, right? So when mass bends light, according to Einstein, that bending is sensitive to all of the matter there is, not just the visible lit up matter. So by using that gravitational lensing technique, we can work out how much matter is in the way when we look at distant galaxies. So that's one way. Another way is to look at rotation curves of galaxies, which is what Vera Rubin did already in the 70s. And there, like if you look at the solar system, right, the further and further away you are from the sun, the planets take longer and longer to orbit, right? So the velocities with which the planets rotate around the sun goes down when you go out to like Neptune and Pluto, right? Well, galaxies are not like that. The stars in the outskirts of a galaxy, in a big spiral galaxy, are rotating just as fast as the ones close by. But the amount of stars is going down, so there must be matter that you can't see that is actually keeping up this acceleration. And that is the current picture. There are many other ways that we have verified that there must be dark matter. We just don't know what is its... We know there's mass, but we don't know what the mass is made of.
Wonderful. Oh, have you got one sneaky one more?
There's one more.
Just a sneak, it has to be a quick one.
Sorry, yeah, I'll make it quick. Thanks very much. It might be slightly out of scope, but from what I've heard, I think one of the big mysteries of the universe is related to things like why are some of our fundamental constants the number they are? So why is the gravitational constant what it is and stuff like that? Mm-hmm. During your work, have you gained some insight as to maybe why that might be?
I personally haven't. It is true that the constants of nature seem to be very finely balanced to, for example, make stars be able to do nuclear fusion and to make carbon so that life is possible and all of these things. But, there's no explanation necessarily for why that is. If you want to read philosophy about this, I recommend my colleague Martin Rees, who has written many books about this. I'm not a philosopher. So, I mean, if you just want my opinion about this, I think, if the universe wasn't like conducive to stars and to making carbon, we wouldn't be here to observe it. So that's called the anthropic principle. It's very unsatisfying, but we do what we can. Yeah.
Brilliant. Thank you all so much. And a huge thank you, Hiranya. Thank you all for coming.